Hi, thanks for joining us today. Welcome to Advanced Manufacturing Media's webinar series. My name is Sarah Webster, and I'm the Editor-in-Chief of Manufacturing Engineering Magazine. I'm very excited to host today's webinar, What's New with Lasers, with Ronald D. Schaefer, CEO of Photo Machining, Inc. in Pelham, New Hampshire. Our sponsors today are IPG Photonics, LaserMech, Miyachi America Corp., Prima Power, Rofen Basel, Schmidt Marking Systems, Technofor, Trumpf, and Tsugami Rem Sales. At Manufacturing Engineering, we're increasingly focused on the role of lasers in manufacturing. We've recently added a laser channel to our website at advancedmanufacturing.org. You can find the content from our recent laser supplement, which was published in July, there as well. Today, Ron is going to talk broadly about all the great advances in industrial laser use, with a special emphasis on his area of expertise, which is micromachining with lasers. Ron is a member of SME's industrial laser community, which is one of the great resources we have here at SME, a highly knowledgeable community of experts. You'll be able to ask Ron questions after his presentation using the Q&A box that will appear at the right of your screen. Time permitting, these will be answered following the presentation. If time runs out before we can get to all of the questions, we will make sure that Ron emails the answers to you. And with that, I'll pass this presentation over to Ron.
Thank you, Sarah. As Sarah said, I'm Ron Schaefer, CEO of Photo Machining. We're a small job shop and systems integrator in New Hampshire. Maybe more importantly, I'm also on the editorial board of Industrial Laser Solutions, which is the largest industrial laser magazine in the world. And I write a column in Micromanufacturing magazine. I've been working with lasers for over 25 years, and in addition to the above, I write a lot of articles, do a lot of webinars, and actually published a book called Fundamentals of Laser Micromachining. And so I want to share some of this stuff with you today. Okay, first of all, why should we use lasers? There's a lot of useful characteristics that lasers have that make them very interesting for manufacturing environments. First one is that they're non-contact. So the nature of the non-contact means that you are minimizing the chance of destroying your part, or you're minimizing the chance of ruining your, for instance, drill bits or router bits or saw blades. So non-contact is a very important part of the laser effort. Also, there's a broad range of output powers available, anything from 1 watt up to kilowatts of power, or tens or hundreds of kilowatts even in some cases. There's a broad range of wavelengths available. So lasers operate for manufacturing purposes from the infrared at about 10 microns wavelength all the way through the UV to about 190 nanometers wavelength. There's a broad range of pulse lengths. Lasers work anywhere from femtoseconds, which is an extremely short pulse length, to the CW, which is essentially like a light bulb. The light is turned on all the time. There's a broad range of repetition rates available. Lasers can work from either 1 shot or 1 hertz, which is 1 pulse per second, up to tens or hundreds of megahertz. There's a lot of different kinds of lasers available, and this means that they're very flexible. So a laser is not a laser. Okay, there are many different kinds of lasers available, and you have to use the right laser for the right situation. One of the neat things about lasers is that new laser sources are constantly being developed, so we have a lot more options as the years go by. We have a lot more options today, for instance, than we did even 10 years ago. So let's look at some laser power levels to get a feel for what kind of power levels we need. If you look at your typical laser pointer that you might use in your desk or to play with cats, it's about 5 milliwatts of output. The typical power level for a laser marker or a micromachining system is about 5 to 100 watts. Typical lasers that you see at the trade shows are usually about maybe 60 to a couple of hundred watts, and even maybe to a couple thousand watts at the bigger metalworking shows. But these lasers are pretty readily available to anybody with enough money to spend on them. In the 1 to 1,000 watts, or even a couple thousand watts, you've got the typical power levels for most machining applications, including welding. The 1 to 10,000 watts is more high-power applications like heavy steel cutting or welding and cladding. And then when you get up to 100,000 watts, that's about the largest laser that's currently ever been made. Only one thing about that, it's a nice laser, but how do you use 100,000 watts? Just the beam delivery itself is very challenging. And if we're going to go into the next step, which is using lasers to shoot down strategic targets such as ballistic missiles, you need about 1 million watts of laser energy. And we're not quite there yet, but we're working towards that goal. So let's talk a little bit about some of the laser characteristics that I mentioned earlier. First one is wavelength. As you can see from this chart of the electromagnetic spectrum, lasers operate from about 10 microns wavelength in the infrared, which is a CO2 laser, all the way through the visible portion of the spectrum, and then into the ultraviolet portion of the spectrum, down to about 190 nanometers, or maybe even 157 nanometers if you want to use a fluorine laser. Lasers also have a defined pulse length, especially those lasers that are used for machining or material removal applications. The pulse length is the time duration of the laser pulse. With that time duration is associated a rise time and a fall time. The rise time is usually fairly rapid, and the fall time is usually indicative of some sort of a tail, so you have a slower fall time in most cases. As a general statement, shorter pulses are better for micromachining, and as a general statement, longer pulses, or CW, are better for welding. We can also talk about repetition rate. So the pulse repetition rate of a laser is a regular train of pulses, and it's defined as the number of pulses emitted per second. And so with some lasers that are very high repetition rate in the megahertz, it's important because you need some overlap when you're trying to do large parts. And the higher the repetition rate is, the faster you can move the beam delivery. Also, lasers come out in potentially single pulses, or each of the single pulses that you see in the diagram could actually be a series of small pulses. And this is called burst mode. So you have the possibility to do single pulse or burst mode in many of these lasers. And sometimes there's some advantages to going to a burst mode situation. If we look at this chart, this is a chart that plots pulse duration against wavelength. And you'll see that pulse duration is starting at the femtosecond, or very short pulse length, on the y-axis and going to very long pulse length, or CW. And on the x-axis, we're going from ultraviolet to infrared light. So let's start in the top right-hand corner. If we have infrared photons with very long pulse lengths, or CW photons, those lasers are usually used for welding and joining applications. It's a purely thermal input, and it's used for applications where you desire a thermal input. They're also used sometimes for very heavy metal cutting, but particularly for welding and joining applications. If you come down to the shorter pulse length, getting into the microsecond and even nanosecond, picosecond, and femtosecond arena, you'll see that even in the infrared, these lasers can be used for micromachining. And as you travel further on the x-axis towards the origin, you go further into the UV. And as you go further into the UV, with a shorter pulse length, this becomes the optimal condition for doing micromachining and material removal with very clean results. You'll also notice that in the upper left-hand corner, there's really nothing going on. And that's because there really aren't very many uses, or no uses that I'm familiar with, for long pulse length or CW UV lasers. So typically they're not really used in an industrial environment, although there's no reason why those lasers can't be made. All right, so lasers are used very widely in manufacturing environments. Usually I talk about micromachining, but today I'm actually acting as a person who is going to talk about all of the applications of lasers in manufacturing. So I won't have a lot of time to talk about a lot of details, but I just want to touch on some important points. So we use lasers in manufacturing for things like marking and engraving, for cutting both metals and nonmetals, for drilling holes, for welding, and that's welding both similar and dissimilar materials, for micromanufacturing, including machining and micro-welding, and also for laser additive manufacturing. And these are the topics that we're going to talk about. Let's start with laser marking and engraving. Marking generally means that there's little or no material removal, and so it's a color change. You can also do engraving. Engraving means that you really have some substantial material removal, and that's actually part of the mark. So there's some material removal to some required depth in an engraving situation. Together, these two are probably the largest market for lasers, certainly in terms of units sold and possibly even in terms of revenue. There's a lot of sheet metal cutters out there which are very high dollar items, but there are many, many, many more markers. So in general, I wouldn't be surprised if the revenue is very close on both of those, but certainly in terms of units, laser markers are by far and away the leader. Generally, though, laser marking is a fairly mature technology, so there's fairly low margin and a lot of competition. Now, for marking lasers themselves, most of the marking these days is done with 1-micron solid-state lasers, typically fiber lasers. These are used mainly for metals and plastics. Or with the 10-micron CO2 laser, which is used primarily for organics like wood, leather, and things like glass, foam, stone, and plastic. The shorter wavelengths like green or 532 nanometers and UV are reserved for applications that require very high absorption, low material impact, and or small marks. And I should probably add one more thing. They're also reserved for applications where cost is not a primary consideration, because it does cost more to make marks with these kinds of lasers because the lasers cost more and they're slower. And another thing I should point out about marking is that in most cases, marking doesn't add any value to the part. Marking just gives you an identifier, an alphanumeric or a logo or something, which is an identifier, but it really doesn't add any value to the part, except in the cases, for instance, like graduating catheters, where the marks are actually graduations that are used. So you have to be careful about marking, because usually the product doesn't have a whole lot of cost built into it associated with the marking process. So here's some examples. The first one shows some engraving, where the surface removal is down to some depth, and you're basically removing material to this depth and leaving something behind that you can feel. In a lot of applications, the fact that you can feel this is not only not undesirable, in some cases it may be desirable. There are a lot of other applications, though, for instance, a catheter that you stick in a human body, where you really don't want to have any sort of feeling or texture on the thing because it's going past sensitive areas. The lower marking application shows the removal of a thin layer of some material, paint, whatever material, anodization. This is another common characteristic, where we just go through a very thin layer to expose the layer underneath, and that gives us the mark. We also talk about things like foaming, where basically the material is heated and you change the surface structure of the material, typically by making it more porous. We also have color change. A lot of plastics just change colors when you hit it with laser. Unfortunately, you don't know what color it's going to be, and you don't really have a whole lot of control over that color. You pretty much, in many cases, get what you get. Fortunately, most of the color change is either white or black, and that's what most of the market requires. However, there are ways to make color changes, especially in metals. If you use the laser cleverly, you can affect the surface oxidization or the surface carbonization. And these can result in different colors being formed on the part. And again, this is typically done with metals. Again, some more marks. You'll see them, and in this case, especially the one in the middle, you find a graduated device, which the marks are obviously part of the functionality of the device. Whereas in the upper left-hand corner, those marks are really not part of the functionality of that device. They're just on there for traceability and perhaps marketing. A few more examples. These marking lasers are used in many industries all across the board. The microelectronics industries, is a big user of them. Medical industries, they're used for making identification cards, for making credit card identifications, passports, a lot of different things. So marking is very ubiquitous, and it's been around a long time, and it's a reasonably mature technology. So let's go on to laser cutting. It's a very large market for flatbed sheet metal cutters. Thousands of lasers or systems are made globally, making large parts and small parts. The basic technology is pretty mature, but the new engineering advances in lasers, in motion control, and in software, and also in part handling, make the newer systems more productive. And specifically the fiber laser coming on the scene, if you would be talking 10 or 15 years ago, most of this cutting was done with neodymium YAG lasers. Now fiber lasers have taken over most of the metal cutting applications, and that's because fiber lasers have a much, much higher focusability, so you can get a higher energy density on part with a lower power fiber laser than you can with a CO2 laser. We'll see that in a few slides. So cutting lasers. As I said, fiber lasers are around. They're efficient. The beam delivery is through a fiber, so that's a very efficient beam delivery. Very high brightness, very high focusability, and high power mean that you have a very high energy density at the part. Disc lasers also around. Disc lasers are fairly similar in performance to fiber lasers. The photons are generated in a slightly different way, but they're similar in performance to fiber lasers. Direct diodes are somewhat of a newcomer on the market, somewhat of a poorer beam quality than you get with a fiber laser and a disc laser, but extremely high efficiency, something like 45%, where fiber lasers are probably in the 30+% range. CO2 lasers, they're still used for many applications, like cutting organics and the thicker steels. And then again, the UV, the ultraviolet, and the ultra-short pulse lasers are used for very small, thin, high-quality parts with minimal thickness and with high tolerance for heat affected zone, and also with, let's say, the cost is not critical. So here's some power density comparisons. If we look at the sunlight, we're getting about 0.1 watt per square centimeter. If we look at a light bulb, it's about 1 watt per square centimeter. The soldering iron is about 100 watts. Okay, an unfocused beam from a 4,000 watt CO2 resonator, that's just the beam coming out of the laser, is about 2,000 watts per square centimeter. If we look at that beam and focus it down, we'll get 30 million watts per square centimeter with a 4,000 watt CO2 resonator focused beam. If we take that same focal length lens and focus a fiber resonator down and a 2,000 watt fiber resonator at that, we'll get 1 million watts per square centimeter. So you can see the fiber resonator is much higher focusability for a lot less output power. And just for example, or for a matter of information, the vaporization of steel occurs at about 2 million watts per square centimeter. So the CO2 versus the fiber laser for this conventional cutting. The CO2 is very versatile. It's been around a long time. It cuts plate steel, a thick steel, very well. It's fairly economical. However, the fiber laser is very fast and thinner material. It's got lower operating costs and lower maintenance costs. So it has pretty much taken over in a lot of the thinner metal application and many of the other application areas. Another thing to note about these cutting applications is that typically with a fixed beam cutter, you're using some sort of an assist gas. And this assist gas can be anything, but it's principally either nitrogen, oxygen, or shop air. Typically the nitrogen and the shop air will be used at very high pressures, and typically the oxygen will be used at a much lower pressure. But a lot of this depends on the kind of metal that you're processing, or maybe it's a non-metal, so the kind of material that you're processing, the focal length of the lens, and exactly what laser you're using. But in general, assist gas is almost always used with fixed beam cutting, certainly in the infrared and even in the UV. And there's a picture of a Cincinnati laser cutting through an inch of steel. Okay, some more cutting examples. We can talk about flat part ODs, internal features. So these are smaller cutting examples, not the thick steel that I was talking about earlier. We make things like gaskets. Stents is a very big market for lasers, both metal and bioabsorbable stents. Organic material can be cut with lasers. Bone saws, connective plates, tube cutting, cutting of nonmetals for many different applications. All right, so let's talk about laser drilling. We just talked about laser cutting, and basically laser drilling is a subset of laser cutting, but you're just cutting in circles, or at least in some sort of closed shapes. The mechanisms include melting, evaporation, and ablation, sometimes in combination, and the correct laser is chosen based on the material you're trying to drill, the absorption at certain wavelengths, the thermal conductivity, and the size of the hole that you're trying to make. I should point out that if you want to make a very small hole, you can't do that with a red laser. You have to use a UV laser because you can make smaller holes with shorter wavelength lasers. So laser drilling advantages and disadvantages. Advantages, there's a shorter process time, less expensive fixtures, easy to change the hole diameter and location by the software. And that can be used on non-conductors or basically any kind of material. The disadvantages are potentially thermal damage to the material. I put a question mark there because, I mean, it depends on what laser and what material. Sometimes you don't get thermal damage. It depends. There may be some post-processing that's necessary. There may be harmful vapors coming off. For instance, if you're cutting something like beryllium, copper, or nickel, or some organics. And one of the bigger initial disadvantages is the initial capital cost. So some comments about laser drilling. Beam quality, wavelength, focal length, and input beam diameter all influence the spot size and the depth of field on the target. The spot size, in principle, if you think about it like a drill bit, is your drill bit diameter, and the depth of field, in principle, is your drill bit length. As I said, assist gases are used to protect the optics in many cases, just from the stuff splattering up on them. They're also used to cool the part. They're also used in, for instance, O2, oxygen-assisted removal, and in the case of N2, they're used to reduce oxides on the surface so you can get a nicer cut. You can pretty much easily achieve the 20-to-1 aspect ratio with near zero taper, and you can get even much higher than 20-to-1 depending on a lot of factors. You can achieve fairly high aspect ratio. As I say, over 20-to-1, you would typically get some taper, but you're usually looking at something like 5 to 10 degrees taper, maybe more depending on the lens, the material, and the laser. As you go smaller in kerf size and thicker in material, the aspect ratio increases and the degree of taper also increases, as a general comment. So some examples. One of the big examples is drilling holes in aircraft engine components. And this is a huge operation where basically you're drilling these holes for purposes such as cooling, for airflow dynamics, for noise reduction. There are several kinds of materials that are used. In general, mostly the materials are metals, and these are drilled with either the YAG laser or a fiber laser in the fundamental wavelength. There are other materials that are used in these aircraft engines. Primarily, some sorts of zirconious ceramics are used to coat some components for heat shields. There are also components made out of carbon-reinforced epoxy. And these carbon-reinforced polymers are actually becoming extremely important, and it's a very big investigation of areas right now, how to cut them, how to drill them, how to weld them, because a lot of different materials in especially flight components and racing cars, things like this, are looking at to be made out of non-metals. And by the way, when I say hole, usually you think of a round hole, but it's not always true. Not all holes have to be round. And in this case, in many cases, what we see is a non-round hole going down to a round shaft. So if you look at the upper right, you can sort of see a shaped hole at the entrance, and then the diagonal is a round shaft going through the metal. Big application area with hundreds of lasers making these things, and literally millions of holes per engine. All right, let's talk a little bit about laser welding. This is macro welding. Weld speeds up to 1 to 9 meters per minute are pretty typical. You can go up to about 25. Weld depth of about 16 millimeters or 5/8 of an inch are pretty typical. And you can go up to an inch or more, depending again on the laser. One thing about welding, the part fit up and the fixturing are key elements. So this is one of the big secrets to welding. It's not just how to pick the laser and how to control the laser, but it's really how to get the intimate part fit up. You can also use laser welding with hybrid methods. So there are other methods that you can use in conjunction with lasers that sometimes enhance the operation. These lasers are used abundantly in aerospace applications, in automotive, in mining, construction, and agriculture. Especially the automotive industry uses a lot of these lasers for welding different components on the auto bodies, such as transmission gears, muffler components, axles, and the body components themselves. So for welding lasers, you usually want to use a very long pulse length or a CW laser. You certainly want to use an infrared laser, and these kind of requirements are in nearly 100% of the applications. The lasers that we use are fiber lasers, disc lasers, and diode lasers, these all being the workhorses. All can be fiber delivered, and all can be coupled with long working distance lenses that can be very far from the workpiece. So if you're working in tight spots, this can be minimized by having a long focal length lens. Only a small fraction of the market still uses CO2 lasers, and as I said, the fiber lasers are taking over more and more of this market. Speed and reproducibility are excellent, and one of the cool things about lasers is that dissimilar materials can also be welded. So some examples. There's some deep penetration welds of stainless steel and copper. The stainless steel shows a weld of over an inch, and the copper shows a very nice weld of about 3/4 of an inch. Some more applications. High beam quality makes a deep and narrow weld, especially if you have a long focal length lens that you're using it for remote welding. Many different kinds of applications for these welding lasers. There's a picture of welding the laser power, or the welder of the powertrain in an automobile. So when we talk about remote welding, for instance, we use remote welding using a galvo head and beam steering. You can do this with a fiber laser because the fiber laser has such good focusability and such a bright beam. This kind of welding saves time because you don't have to move the laser head with each weld. You can just move the galvo, and galvos are much faster than robots or anything else. Fiber lasers have good beam quality. They use long focal length lenses, very fast in the welding. And you can also customize weld patterns for optimal joint strength. So the options are somewhat unlimited. When we do remote welding, just like when we do any other manufacturing process, we have to, number one, have precise fixtures. And part of that is precise fixtures which make intimate contact. We have to have some sort of a gas assist. And we want to have also some sort of a Class 1 enclosure so that while the processing is going on, it's not a danger to the operators and the people in the room. All right, so let's talk about some emerging laser areas. Ultra-short pulse lasers, some micromachining applications, some 3D printing, which is a very hot one, and also some other interesting applications. So ultra-short pulse lasers. Short is a relative term. So when I talk about short, I mean less than a nanosecond. And so that includes the picosecond, which is 10 to the minus 12 seconds, and femtosecond lasers, which is 10 to the minus 15 seconds. It potentially even includes even shorter lasers, but below about 150 femtoseconds, the optics become very challenging. And so, except in very specialized cases, I don't really see any manufacturing in the near future using lasers less than 150 femtoseconds, unless it's a very special thing. Very, very high peak powers, though, even with low pulse energy because of this business of the short pulse length. And so if you have a small spot size, you can get high peak power intensity on the target. Some general observations for the picosecond regime. Generally, pulse lengths between about 50 picoseconds and 1 nanosecond aren't very useful in general, but there are some specific applications that they seem to be useful for. At 10 picoseconds, there's definitely a difference in the quality between the fundamental, doubled, and triple wavelengths for almost all materials. So this business of whether 10 picoseconds is short enough to not show any wavelength effects, not on most materials. You definitely see the wavelength effects. For most USP applications, though, picosecond is good enough. You don't need femtosecond lasers. And higher powers are commercially available in picosecond than in femtosecond, unless you use a really big and expensive amplifier. Now, there are some customers who are making some very large orders, for instance, Apple and Foxconn, and they're ordering hundreds of lasers at a time. The problem is these lasers have very aggressive deliveries. And so when a customer calls up and says, I want to order 100 lasers, and I need them in the next 6 months, this pretty much keeps the smaller players from entering the market. So even though there's a couple of dozen companies now making picosecond lasers for manufacturing, only a couple of them are large enough to actually take delivery on these big orders. General observations on femtosecond lasers. At 300 femtoseconds, for most materials, there's very little difference in the quality between the first, second, and third harmonics, especially in metals. However, there are some materials like glass and polymers that are still best processed with the UV. Even though femtosecond is usually a better choice for quality, again, as I said before, probably the majority of the applications, picosecond is good enough. In any case, UV photons still always give a smaller spot size, so if small is key, you really need to use UV even in the femtosecond regime, even if it's not for the purposes of quality, but for the purposes of a small spot size. And then the other thing is, because these beams are so bright with a short focal length lens, you typically get air breakdown, so a purge may be necessary. So micromanufacturing with lasers. I define this as feature sizes less than 1 millimeter, material thickness less than 1 millimeter, and usually both a lot less. It includes additive joining applications, deposition, and welding. It includes marking. Must use lasers, but it does not include applications where the photons touch the skin. So when we talk about medical applications, we're generally talking about medical devices, and especially disposable medical devices. We're not talking about surgical applications, although they certainly do exist. Micromanufacturing lasers generally have low power, less than 100 watts. For the smallest features, you use the UV or the short wavelength and or USP lasers. And for the larger features, IR might do, and it's cheaper. For joining applications, you use infrared. So, some examples. Micromilling, PCT grooving for ultrasound, microfluidics devices. This is a very, very big application area. And we see this as a growing application area. You can see some of the microfluidic devices on the bottom of this slide. Micromachines for insulin pumping, for instance, or brain probes, which I'll show you an example of later. Micromolds for injection molding. Lab on a chip, another big application area. And shaping of catheters by drilling holes for drug delivery or tips for insertion is also another very big application area currently. Here's some micromechanical parts. On the upper left, you'll see a bioabsorbable stent. These bioabsorbable stents are made with short wavelength and or short pulse length lasers because they're actually heat sensitive since they're made to dissolve in the body. So if you have any heat in the laser process, you can't make a bioabsorbable stent. They're very sensitive to heat. On the top right, you'll see 3D features in polyimide. Those streets are about 10 microns wide, and the bumps are on the order of about 30 microns. So we made these extremely small features in a piece of polyimide. On the bottom, you'll see a gear that was cut out of a piece of plastic and with respect to a Lincoln penny. And this gear was taken right off the laser, so it's fairly clean right off the laser. More examples of laser cutting. We can use tube cutting for cardio and neuro stents and for surgical needles. We can use tube cutting for biopsy probes and cannulae. Again, big application areas for these kinds of lasers currently. One of the biggest, or probably the biggest, is stents, manufacturing the different kinds of stents out of metal for deployment in the body. On the upper left, you see an undeployed stent, and on the right and on the bottom, you see different versions of deployed stents. from different manufacturers. And sometimes metal stents aren't going to do the job. There's some drawbacks with metal stents because once they're in there, if you have a problem, you can't just take them out. Well, polymeric stents stay in the body for a few weeks and then dissolve. So the hope is that they stay in long enough to keep the occlusion open until the problem goes away. But the nice thing is, if the problem reoccurs, you can just stick another one of these polymer stents back in. You don't have to take the old one out. And that's what some of the real interest is in these polymeric stents. Plus, you won't set off the bells when you go through the metal detector in the airport. Laser cutting of non-metallics. We can also cut things like ceramics. We can cut glass. We can cut plastics. We can cut nylons, rayons, Teflons, just by using the right laser. All of these different materials can be cut with high quality and fairly high speed. So some micro drilling. Some examples include drilling for drug delivery, catheters, angioplasty balloons, inhalers, insulin dispensers, connective plates, flow cytometers, flow regulators, microfilters. I've talked about some of these things, but you can see on the lower left figure, the thing that kind of looks like a little flexible funnel is actually a blood filter. Some more laser drilling, again, catheters, microfluidic devices with small holes in material used for different chemical analyses. Microvia drilling is a very big application area. Your cell phone would not exist without lasers. Lasers are used to drill the conductors in all of the printed circuit boards and flexible circuits in a cell phone and in other high-tech devices. And then this is a picture of a catheter that shows holes that were drilled for drug delivery. Some welding and brazing examples used in a lot of things like endoscopes, pacemakers, welding of dissimilar metals or welding of dissimilar materials, plastics, different plastics to each other or different plastics to other materials, and also louver attachment. So laser welding. We can use them for instruments, for disposable probes. Batteries is a very, very big application area. There's a biopsy probe. Those are welded with lasers, dissimilar materials here, and batteries. Like I said, batteries is a very big application area for lasers, and it's becoming more important because primarily there's a lot of dissimilar materials in batteries that need to be joined together, and lasers are a very good way to do that, sometimes the only way to do that. Hermetic welding of pacemakers. There are something like 80% of the pacemakers in the world are manufactured in Puerto Rico, and there are tens of systems there doing nothing but welding these pacemakers. By the way, there's something about welding that we should talk about. Usually, or in many cases such as this, welding is the last step in a process. So there's already a whole lot of value going into a part like a pacemaker, and so you don't want to screw it up because this is the last step in the process. So the yield has to be very high. Defibrillators is another thing that we use laser welding on. You'll see a neurostimulator here. Now that's currently the state of the art where you have the brain probe going into the brain and there's some sort of a wire going down to a battery pack and a brain, let's say, or its own brain on your chest. However, that's kind of awkward. You've got the thing kind of hanging down and you've got this thing glued to your chest. The next generation of these devices, everything will be so small it'll fit into the package about the size of a dime so that you can actually carve out a section of the skull, put all this stuff in the section of the skull, and you won't even see any of this stuff. Another growing market, huge growing market, is 3D printing. Very big growth potential. You see these printers, these companies everywhere. The companies that have the biggest market share are Stratasys and 3D System. They hold the lion's share of the market. However, this market is using devices other than lasers. There are more technologies available, but the laser-based technologies are, in general, the fastest, the most accurate, and the highest resolution. They're also the costliest. There are also some material limitations, and limitations meaning either availability or sometimes the cost, but these will be overcome. So Stratasys and 3D Systems have the lion's share of the market, but EO Systems, a German company, basically makes the high-end laser additive manufacturing systems. So there's essentially two technology choices. In the one, you feed some material into the beam path, either using a spray, a jet, a ribbon, or whatever, and that's deposited on the part. In the second one, you have a part and you squeegee a layer of material, and then you do your laser processing, and then you lower the material, squeegee another layer, do the laser processing, lower the material, squeegee another layer, and you do this in fine layer, and then the laser only exposes and hardens what it hits in the beam path. So if you look at the upper right, you'll see the laser actually exposing and sintering some metal on a powder bed. And if you look on the lower right, you'll see the finished part, basically. And the finished part has all kinds of little internal chambers and things that you could never make with any other kind of machining process. So you're able to do things you can't do in any other way using 3D manufacturing. All right, let's talk about some system costs. Laser markers are typically about $20,000 to $70,000. Laser micromachining in the IR, $200,000 to $400,000. Laser micromachining systems in the UV and the USP range between about $400,000 and $600,000, and laser welders come in about $70,000 to $200,000. Generally, though, you get what you pay for. And by the way, those numbers can go way up from there depending on the automation and depending on the size of the laser. If you put a 10 kilowatt laser in one of these systems, the price is going to go into the $1 million range. I like to show this graph. This is a graph of market maturity with respect to time. It can also be a graph of technology maturity. Take your pick. Usually at the start of a technology, you'll see where I have entrepreneurs run the company. This is when technologies first come out. There's only a few people doing this kind of thing. Your options are limited, and new kind of cool stuff's coming out every day. So as the market matures and you go up that curve, basically what you have is that the technology matures faster than the market matures. When you get to the plateau and compete on price, you have a lot of players in the arena. You're generally selling off of spec sheets. You're competing very heavily on price. And at that point, you have more of an accountant-run company than you have an entrepreneurial-run company. And if I look at some of these things we're talking about, I think ultra-short pulse machining is right still on the very early stages of the market maturity curve. I think laser micromachining is about halfway up the market maturity curve, as well as laser additive manufacturing. And typical marking, drilling, and cutting, and welding and joining are pretty close to the plateau. All right, so final thoughts. First of all, lasers are currently being used in many different markets and manufacturing environments. However, a laser is not a laser. There's all kinds of different lasers out there with different pulse lengths, different rep rates, different everything. So you need to use the right laser for the job. Lots of new players are coming on, so there's a lot of more choices, and the costs being driven down on a dollars per watt basis. A very important point. You can spend all the money you want on the most expensive and fanciest laser imaginable, but if you don't use it correctly, you won't get the proper results. So you need to have good beam delivery and use it correctly otherwise. Unfortunately, we wouldn't get a chance to talk about all those things in this seminar because there just isn't enough time. Lasers are also used in other markets, not just manufacturing. And for us laser guys, the coolest markets are the markets where lasers are not only better, faster, and cheaper than other technologies, but where basically they're the only technology that'll do a job. And so in conclusion, I'd like to hope that I've convinced you that lasers are really cool. They're found in a variety of different manufacturing roles, from the macro to the micro, in the cutting, welding, drilling, structuring, marking, and so on. They're also used in non-manufacturing environments, such as surgery, light show, alternate reality environments, games, and defensive and offensive military weapons. New laser sources are continually being developed, which extends the range of the laser uses, and the laser powers are increasing and the cost per watt are decreasing with time. Finally, I'd like to acknowledge my colleagues who've given me some of the slides that you've seen. Hopefully you've noticed that the slides have the companies on that they represent: Dan Gold from LN Laser, David Cratley from IPG, Neil Ball from Directed Light, Dale Sabo from ScanLab, Jeff Shannon from Miyachi, and Rick Neff from Cincinnati. Thank you very much, guys, for all your help, and thank you for your friendship over the years. And Sarah, I'm going to turn it back over to you.
Thank you so much, Ron, for that informative session. As Ron has shown, industrial laser use continues to become more advanced and useful for a wide variety of applications. We're going to try to get to a few questions here, and if for some reason we don't get to your question, we will answer it via email. If you have a question, I'd like to encourage you to send it on the Q&A bar right now, but we do have a couple already in the queue, so I'll get right to it here. Ron, with increased emphasis on lightweighting across the motorized vehicle and aerospace industries, with a lot of composites and laminated composites, why are lasers well suited to cut those materials? And do you think that we're going to see more of that?
Well, yeah, we're actually going to see more of it, definitely. And the reason that lasers, and I'm going to put that word in a quote, lasers are suited to this is because there are so many different kinds of lasers. So you can choose the right laser that has the right wavelength, the right pulse energy, the right repetition rate, and choose that laser that is necessary to do the job that you want to do. With a lot of other technologies, you don't have the flexibility that you have with, again, lasers in quote.
Okay, our next question comes from a gentleman who works for Whirlpool, and he asked the question, in our industry, plain carbon sheet steel substrate is used with hot-dipped galvanized coating. With laser cutting, is there a zone near the edge that loses all galvanic protection?
Wow. I'm going to have to say I don't know the answer to that, but if you just send me the question by email, I will talk to my friends in the industry, and I will see if I can get an answer for you there. You stumped me on that one.
Okay. We have, you mentioned in your presentation that ultra-short pulse machining is lower on the market maturity curve, and therefore there's still a healthy amount of innovation and development in that area. What does the near-term future hold there, in your opinion?
I can actually answer that pretty accurately because I polled about 30 different companies that make pico and femtosecond lasers just a couple months ago and asked them to tell me, what they're doing and where they're going. And basically the answer that I got are as follows. Number one, more power. Number two, lower price. Number three, smaller box. And number four, potentially in the cases where those manufacturers are only in the fundamental wavelength, potentially going to the shorter wavelengths.
We have another question about the pulse tail that you mentioned. How critical is the length of the pulse tail, and does it impact welding, cutting, etc.? What's its importance here?
Well, yeah, that's actually a good question too, because I didn't really go into a whole lot about the shape of the pulse. I showed you a general shape of a pulse. For micromachining applications, if you wanted a perfect pulse, I guess in principle it could be somewhat Gaussian, but an even better one is a square wave. So if you really had a square wave pulse, that would be the optimum. Unfortunately, that's not how the pulses come out of lasers. They usually come out with a fast rise time and a long tail. Now, Spectraphysics has a option in their lasers, or at least in some of their lasers, where they can actually tailor the shape of this pulse to make it with a longer tail, a shorter tail, a Gaussian profile, or whatever. So yes, it does make a difference on the part. In most cases, you don't really have control of that. It kind of is what it is. But in some cases, manufacturers do give you the option to control that pulse to some degree.
Another question for you here. Are the new CO2 lasers using less gas to produce the beam?
Well, I would say that's as a general statement, that's still a fair statement, yes. Look, even, let's say 20 years ago, you really didn't have much in the way of sealed CO2 lasers anyway, just low-power sealed CO2 lasers. Almost all the lasers were some sort of flowing gas, at least the higher power ones. So I would say yes as a general statement, but they still use a lot of gas.
We have a question about welding here. So some of the welding images that you showed during the presentation were joining thicker material to thick material. What about joining thin material to thick material, say 2/100 thick to 1 inch thick material? Is that something fiber lasers are well suited for? What is your recommendation in that area?
I'll say right up front, I'm not a welding expert, but I see no reason why that should be an issue. If you use the right laser and the right power level, I don't see why you couldn't be able to measure or weld thin materials to thicker materials. In fact, I think it's probably more challenging to weld a very thin material to another very thin material.
We're getting close to the end here of our presentation. A number of you have asked whether you can get the presentation, and we will be sending out a download link for that, so just so you all know. We have another general question here. What is the difference generally between a YAG and fiber laser?
Okay, well, the main difference is the focusability, basically. So if you have a fiber laser of the same output power, basically, you'll have a lower M squared in general, and that means with the same optical setup, you can get a smaller spot size, which means that you have higher brightness on the part.
Okay, and now we're on to our final question here. Can you change the laser marking color on plastic by varying the laser beam intensity or the type of laser?
I'm not an expert on colored marking, but my reaction would be it would be very difficult to do that. So I would think that only in very special cases with maybe some special plastics, possibly that were even formulated to do that sort of thing.
Okay, well, that's all the questions we have time for. Thank you, Ron, so much for your excellent presentation. If you still have questions or even have questions after this webinar, feel free to email me directly at swebster@sme.org. You can also connect with our team here at FabTech in Atlanta, November 11th through 13th, and we encourage you to stop by our website, advancedmanufacturing.org. Thank you so much for joining us for this Advanced Manufacturing Media webinar. We hope you found it informative, and have a great day.